terrestrial planets. These are the rocky worlds of our universe, made up mostly of solid surfaces, metals, and silicate rocks. In our own solar system, Mercury, Venus, Earth, and Mars fall into this category. They form closer to their host stars, where the intense heat prevents gases and ice from clumping together, leaving behind heavier materials to crash and fuse into dense spheres. Because they have a solid surface, they are the primary targets when scientists search for places that could potentially support life. Gas giants. These massive spheres are composed primarily of hydrogen and helium, swirling in endless, chaotic storms without a true solid surface. Jupiter and Saturn are the famous local examples, holding on to vast atmospheres through immense gravitational pull. They form much further away from their stars, out in the colder regions where lighter gases can accumulate around a rocky or metallic core over millions of years. Their sheer size often dictates the gravitational balance of their entire planetary system, pulling in or deflecting asteroids and comets away from the inner rocky worlds.
Ice giants. While similar to their larger gaseous neighbors, these worlds contain a much higher percentage of heavier elements like oxygen, carbon, nitrogen, and sulfur, which astronomers group together as ices. Uranus and Neptune sit proudly in this category, showing off deep blue and cyan hues from the methane in their atmospheres. The term ice is slightly misleading, as these materials exist in a highly compressed superionic fluid state deep beneath the cloud tops. They represent a unique middle ground in planetary formation, growing large enough to capture some gas, but not nearly as much as true gas giants. Dwarf planets. These are celestial bodies that orbit a star and have enough mass to form a mostly round shape, but they have not cleared their neighboring region of other debris. Pluto is the most famous member of this group, having been reclassified after astronomers found many similar objects drifting in the outer reaches of our solar system. They often reside in crowded neighborhoods, like the asteroid belt or the Kuiper belt, sharing their space with countless rocks and icy comets. Understanding them helps scientists piece together the leftover building blocks from the early days of solar system formation. Exoplanets. This is a broad term for any planetary body that orbits a star outside of our own solar system. Thousands have been discovered since the early 90s, using incredibly sensitive telescopes that watch for tiny dips in a distant star's light as a planet passes in front of it. They come in an astonishing variety of sizes, compositions, and orbits, proving that our arrangement of planets is just one configuration out in the cosmos. Finding them has revolutionized astronomy, turning the theoretical possibility of other worlds into an expanding catalog of real places. Hot Jupiters. These are massive gas giants that share the physical characteristics of our Jupiter, but orbit extremely close to their host stars, sometimes completing a full year in just a matter of days. Because they are baked by intense stellar radiation, their atmospheres swell and reach scorching temperatures. Astronomers were initially shocked to find them, as traditional models suggested large gas planets could only form in the freezing outer edges of a star system. It is now widely believed that these giants formed far away and slowly migrated inward over time, dragging through dust and gas until they settled into their blistering, close-quarters orbits. Super-Earths. These are rocky worlds that are significantly more massive than our own planet, but still lighter than the ice giants. The name only refers to their size and does not imply that they are habitable or share Earth's pleasant climate. Some might be covered entirely in deep oceans of water, while others could be barren rocks enveloped in thick, suffocating atmospheres.
They appear to be one of the most common types of planets scattered throughout the Milky Way. Yet, curiously, our solar system does not have a single one, leaving scientists to study distant examples to understand how they function. Mini-Neptunes. Sitting slightly larger than super-Earths, but smaller than true ice giants, these worlds possess thick atmospheres of hydrogen and helium wrapped around a dense core of rock or ice. They bridge the gap between rocky planets and gas-dominated worlds, a planetary size missing from our own local neighborhood. The immense pressure inside their thick envelopes would make the surface completely inhospitable, likely compressing deep layers of water or ice into strange, exotic states of matter. Observing them gives astronomers crucial data on how planetary atmospheres form, strip away, or survive under different stellar conditions. Rogue planets. Instead of orbiting a star, these solitary drifters wander completely alone through the freezing darkness of interstellar space. They were likely born in normal solar systems, but were violently ejected by the gravitational disruption of other massive planets passing too close. Without a star to provide heat, their surfaces are frozen solid, though some scientists theorize that internal geothermal activity could keep subsurface oceans liquid under thick sheets of ice. Detecting them is incredibly difficult, since they emit no light of their own, requiring astronomers to catch the brief moment their gravity bends the light of a distant background star.